The Sun is a middle-aged star, halfway through its lifespan. When it runs out of fuel, it will swell to 200 times its current size, swallowing Mercury and Venus, and likely Earth. Every structure humans have ever built, every record of our existence, every atom of living things will be consumed in the process. This expansion is only the first stage of a sequence that will rewrite the chemistry of our solar system. Currently, the Sun exists in a state of main sequence stability. It functions as a gravitational pressure cooker, smashing hydrogen atoms together to forge helium deep within its core. This fusion generates outward pressure, perfectly balancing the star's crushing gravity. As helium builds, the Sun burns hotter, causing a steady 10% increase in outward radiation every billion years. This chart shows the star's luminosity intensifying. 1 billion years from now, that 10% increase hits a critical threshold for Earth. The rising temperatures will cause the oceans to physically boil. Massive volumes of water will evaporate, turning the atmosphere into a thick, suffocating blanket of steam. This rapid evaporation triggers a massive runaway greenhouse effect. Without liquid water to regulate temperatures and sustain the carbon cycle, the planet loses its ability to support life. The biosphere will collapse long before the Sun ever touches the atmosphere. The countdown for life on Earth is not 5 billion years, but just 1 billion. Our window of habitability is closing much faster than the age of our star suggests. When the hydrogen fuel in the core is finally exhausted, the Sun's internal structure collapses. Without fusion to hold it up, the core shrinks and superheats. This internal collapse paradoxically forces the outer layers to begin a massive expansion. During this subgiant phase, the intense internal heat moves outward. The Sun will brighten significantly, shifting the light spectrum and turning the familiar yellow orb into a much larger, harsher presence in the sky. This diagram illustrates the red giant phase. As the Sun swells to 100 times its current radius, its outer atmosphere will physically cross the orbital paths of Mercury and Venus, incinerating both planets instantly. From the surface of a scorched Earth, the Sun would dominate the horizon. It would appear as a massive, dark red sphere filling a quarter of the daytime sky, radiating enough heat to turn the landscape into a dull, glowing wasteland. Whether Earth is physically swallowed remains a point of scientific debate. As the Sun sheds mass, its gravitational pull weakens, which could allow Earth's orbit to drift outward. The planet might survive as a charred frozen rock, or it might be pulled into the solar fires. Regardless of the exact orbital mechanics, the inner solar system will be rendered unrecognizable. Any protective environment for life will be erased. Eventually, the core temperature hits 100 million degrees, triggering the helium flash. This is a sudden, violent ignition of helium fusion. The star briefly stabilizes, but the new fuel source burns with a desperate intensity. When the helium runs out, the Sun enters its final expansion, the asymptotic giant branch. The star balloons one last time, reaching up to 200 times its original size and pushing its outer layers into deep space. The Sun lacks the mass to end in a supernova. Instead, it will spend tens of thousands of years quietly shutting its outer layers. This creates a planetary nebula, a vast, glowing cloud of gas and dust that drifts away from the center of the solar system. At the center of this nebula sits a white dwarf. This is the dead, exposed core of our star. As this diagram shows, it is roughly the size of Earth, but it still contains the mass of a star. The density is so extreme that a single teaspoon of white dwarf material would weigh as much as an entire mountain. It is a concentrated sphere of matter, glowing with leftover heat. Our life-giving star ends its journey as a silent pinprick of light. It will take trillions of years for this ember to finally cool into total darkness. While the inner planets vanish, the outer solar system experiences a brief thaw. As the habitable zone moves outward, frozen moons like Europa may see their ice shells melt, potentially becoming ocean worlds for a few million years. The atoms shed during the nebula phase don't go to waste. They drift until they collide with new gas clouds. These recycled materials provide the heavy elements necessary to ignite new stars and form new rocky planets. This process links us to the deep past. The carbon and oxygen in your body were forged in the death cycles of stars that existed long before our sun was even born. The destruction of a solar system isn't just an end, it is a necessary manufacturing engine. It is how the universe prepares the raw materials for the next generation of worlds. For us, the timeline is clear. We have 1 billion years before the Earth becomes uninhabitable. If humanity is to survive, we must eventually leave our star behind and find a new home among the lights in the night sky. The sun will die. This is a certainty of physics. But the atoms it scatters when it goes don't disappear. They drift through space. They find new clouds. New stars form, new planets, new oceans, maybe new life. The same atoms in your body right now have already been through this once, and when the sun goes, they'll go through it again. Subscribe to Stellar Abyss. Every Tuesday and Friday we go deeper. The next video is already waiting for you.